Hi. I would like to show you an example of how implicit differentiation works. And in particular, I want to show you an example of finding tangent lines using implicit differentiation. The problem that I'm going to use as an example is taken from your book. It's on page 162, number 17. And in this problem, we're given the relation x squared plus xy minus y squared is equal to 1. And they ask us to find the line tangent to the curve. Actually, they ask us to find the line's tangent and normal to the curve at the point 2, 3. Now, remember that our basic format for this is to evaluate the slope and the point. And for our tangent, our slope is going to be dy dx, or y prime, at the point 2, 3. Notice that this is how we demonstrate that we're evaluating at the point 2, 3. The point is already given to me, which is what s. And this is for the tangent line only. When we come to the normal line, we're going to base that normal line slope off of the tangent slope, because the normal line slope is going to be negative 1 over dy dx. Because tangent and normal are perpendicular, and perpendicular lines have negative reciprocal slopes. So, what our job is to find dy dx. And we have a relation between x and y like so, and we're now going to differentiate that relation with respect to x. Remember that the spirit of implicit differentiation is that if the relation holds, that is, if x squared plus xy minus y squared really is 1, then the rate at which both sides of that equation change with respect to x must always be equal. So our first step in implicit differentiation is to simply differentiate with respect to x on both sides. Now we're going to walk through term by term. The derivative of x squared with respect to x is 2x. The derivative of x times y requires a little bit of special care. Notice that this is a product, and so it's going to require the product rule. First times the derivative of the second, and notice that the derivative of y with respect to x is dy dx, plus the second times the derivative of the first. And notice that the derivative of x with respect to x is 1. I could have written it as dx dx, but that is, of course, just 1. And then finally, the derivative of y squared with respect to x will be 2y, that is the derivative with respect to y, times dy dx. And this was the part that was confusing to some people earlier. Remember that this is just an instance of the chain rule. So that if I have the derivative with respect to x of some function of y, and according to the chain rule, it should be equal to f prime of y times y prime, or f prime of y times dy dx. And that's exactly what I did over here. I took the derivative of y squared with respect to x and evaluated that as the derivative of y squared with respect to y times dy dx. Well, so much for the left side. The right side's easy. The derivative of 1 is 0. Now that I have differentiated, I'm now ready to use the fact that I know the values for x and y at my point of tangency. At my point 2, 3, the x value is 2, the y value is 3, and so I can substitute. X is 2, and y is 3, and all of that is equal to 0. And now it's just just a matter of collecting like terms. I've got some constants here. I've got some terms involving dy dx here. And when I combine them, I get 4 plus 3 is 7. When I combine the dy dx terms, I get 2 dy dx minus 6 dy dx is negative 4 dy dx. And all of that is equal to 0. So this is an equation that's easy enough to solve. This gives me 7/4 as dy dx, and that is the slope of my tangent line right here. Meanwhile, the slope of my normal will be the negative reciprocal of that. But I am not quite done. A couple of you have gotten the tangent line confused with the tangent slope. The tangent line is the equation in the form y minus y1 equals slope times x minus x1. And here I pull in the slope and point from above. Meanwhile, the normal line is going to be also y minus y1 equals slope times x minus x1. But now our slope is the negative reciprocal of the tangent slope. This is the right way to show your work, guys. Clearly identify and label the tangent line and the normal line. Well, I hope